everybody. I assume you guys are here for two reasons. One, the obvious one, is that you like Elixir, and the other one is that you like chess. Well, I do too. And so I'm up here to share with you a story about a dream I had and how that dream was shattered. This is my first time at ElixirConf, so I'm honored that you guys wanted to come here and listen to whatever I'm about to say. First, a little bit about me. I'm Barrett Helms, and I fell in love with Elixir at RubyConf in 2014. There was a talk there by Benjamin Tan Wai Hao, and at one point he showed a graph of like 30 blue spheres all connected to this one red sphere, and he said, "Watch this," and he pressed the button, and all the blue spheres went away, and they all came right back on. And I was like, what? Elixir? This is what we need to do. I was working at a Ruby shop at the time, and all the pain points I was running into, Elixir just solved right out of the box. And so it was amazing. And now I work at a company called SalesLoft, which is a software as a service revenue workflow platform, and I get to write Elixir all day. And so I have found the dream in that regard. I also like Rust, so we're going to use both in this talk. I think Elixir and Rust go really well together. One's a dynamic functional language that blows concurrency and distribution out of the water, and the other one is a safe, statically typed, non-garbage collected, blazingly fast language that you can just escape out into if you need to from Elixir using a Rustler, which just makes it so easy. And then I like to do things and then write about them, and that's my blog, superprofundo.dev. Okay, so the setup. A few years ago, my brother-in-law came up to me and said, "Hey, do you have a chess.com account?" And I said, "No." And he said, "Well, get one and we'll play." And I said, "Okay." And it was shortly after that I became completely addicted to chess. And I just wanted to know how I could get better at it. So I read a bunch of books, and none of them helped because they were very specific on certain parts of the game. And I just needed a general overview of how to get better in all parts of the game. So I eventually found this book by Dan Heisman, and it's perfect for it because no matter what your rating is, it says this is what you should be studying, and these are the books you should be reading to advance to this next range of rating. And one of the books was this one, Chess Tactics. At my rating at the point, which was about 900, studying tactics was the most important thing I could be doing. And it was a specific type of study. So you would get this specific book, and it's got chapters of exercises throughout. And the point is you pick a chapter, you do all 30 or so exercises in a chapter, and you have to do each one in under 5 minutes. And then when you can do that, you start over and you do each one in under 2.5 minutes. It halves at each time. And then once you can do an entire chapter of each exercise in 10 seconds or less, then you move on to the next chapter. And you do this whole book. And then there were several other books that you do the same thing to. And then you can go to the next rating once you get up there. So it's pretty awesome. It's also the same thing as the woodpecker method from this other book. It's the same idea. So I found out what I needed to do, and here's the problem. I didn't want to wait till my children were asleep and go sequester myself in the house and do homework with a pencil going through this book. I wanted to sit on the couch and just whip out my phone and do this stuff and have it track it for me, have it timed, how I do on the cycles, and having it automatically reduce the time and all that stuff. And there was nothing I could find online that I was able to do this for. There are other tactics places you could find, but it's usually whatever they want you to do. It's not doing this procedure of the cycles and having of the time. So I'm a programmer. I made one myself called ChessCrunch. And it does everything that I want it to do on my phone. The new problem is that Now I have to go into each one of these exercises and manually set up the position and then put in its solution and do it over and over again. And I did like 2 chapters, and I was like, this is unsustainable. I can't do this. And then I had my dream. So my dream was to open this up and go psh, 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 and have them loaded for me. Isn't that amazing? All right, end of talk. Well, thus was born chess vision, being able to take a picture of a chessboard and have it loaded for you on your phone in the app. In order to do this, I'll go over the high-level algorithm of this. And if anybody caught Caitlin's keynote, there's a lot of overlap here. I wish I had known what she went over when I started doing this. But basically, you've got a picture, and you need to detect the board in that picture. So the first thing you do is turn the picture into grayscale, because there may be, with grayscale, you only have 1 channel, rather than color, where you have multiple channels. That just reduces the complexity. It's 0 to 1, white to black. Then you can do canny edge detection, among many other algorithms, as she talked about this morning. This finds the edges in a picture. And then hue line transform goes over those edges and determines if they're actually lines. Then when you have those lines of the chessboard, you can find the intersections of them, and then you'll be able to crop those squares into their own individual images. So you have 64 squares at the beginning, or at the end. And the reason I did this in Rust was because I was very naive and I can't think of the word. I was stuck in my dream, and I wanted to do all of this from scratch. I wanted to find out the canny edge algorithm, the hue line algorithm, and study some math papers and write all this from scratch. And I was like, well, this is also unsustainable because I have a talk in like 4 weeks. So I ended up going to use, it's a Rust NIF in the app, but so I started out like that and then went to OpenCV because they just had all the stuff for me out the gate. And it wasn't until after I did all this that I realized that there was eVision, which is Elixir bindings for OpenCV. What do you know? So once you have your square images, then you can classify them. We're back up in Elixir land. We can prepare training data and then predict another image coming in to label the square, or classify the squares, and then you can turn all of that, when you have it done, into a string of Forsyth-Edwards notation, which is a way that a string of characters that describes a chessboard at any given state of a game. But first, to get an image, you need a way to get it. Start up a vanilla live view app that just has a form where you can upload an image. And then when it comes in, save the image, then convert image to fin, which you give it the path of your image, and you'll get a string back that is that fin, and then store that in state, and that's how you can view it. The convert image to fin is where it goes into the NIF and then comes back out again. And here is our picture. One picture from this book uploaded. And that's the starting point. Now we have grayscale. In OpenCV, this is the beginning of the NIF to detect the chessboard. In OpenCV, you can just do imread and then give it a flag that says grayscale. Boom, you've got a grayscale image. Save it so you can show it at presentations. And there's our grayscale. Almost identical, if you couldn't tell. Now we've got canny edge detection. We want to take that grayscale picture and determine the edges in it. And this image prop canny function that I did not write from scratch comes from OpenCV. You just give it the image. These are matrices, by the way, the image, and then you copy it to get a duplicate one because it puts all the edges into that one. And then You've got some arbitrary numbers down there that I don't really know what they mean, but just like Caitlin said, if you play around with them, you can see what they output. There are two thresholds and then an aperture size for a Sobel operator. So whatever that means, you can just move them around until you get the result you want, which is this. And at this point, I was like, this is actually working. I might be able to give a talk on this. So we go to the next part. Hue line transform. Once again, another not original function called hue lines. Take the edges, put them into a new matrix called lines. Then you have row, theta, and a threshold. In hue space, everything's angles. So you've got the row starting point and then the theta starting point, and you get back lines that are modeled after row and theta. And then the threshold is if every line gets a vote. So if all of the votes for that line are below the threshold, it's not counted. Anything above that is counted. Once again, play around with these because the results are wildly different. So the first result of my hue line transform was beautiful. And then so, okay, this is where the playing around with numbers comes in. Second result. Aha! I drew it in red so that I could see the failure. But in this case, the black squares weren't actually black, they're just diagonal lines, and they were overruling any other lines in this image. And it was this point where my dream collapsed like a flan in the cupboard. And I was like, maybe I can't do this. What am I going to do if I have nothing to show for this talk? So I went back to the drawing board and I said, okay, instead of trying to get this out of the image, let's just give it perfect input, pristine input. So I went to chess.com and I cropped a perfect square with 64 perfect squares and images that are all identical except for the color. It's like, let's see what happens with this. Grayscale, good. Edges, well, it's a little hard to see, but they're also good. And then lines, it's exactly what I wanted. I'm back. So now that we have this detection algorithm that will only work for this exact input that is not generic in any way, we can get the intersections of those lines. This is a simple algorithm, just basically going over every horizontal line and then finding out every vertical line where they hit and getting those intersection points. And then you can just crop those using OpenCV. You can make a rectangle with the XY points and the dimensions. That's all perfect dimensions, so they're the same. And give it to matrix ROI, which is region of interest, and it just crops it for you. And then save it and return a list of the file names out of the NIF back into Elixir. And now we have all of our 64 squares. Perfect. And this is the part. This part is actually more interesting and fun than the detection part, which I thought the detection part would be more fun, but it wasn't. Working with NX and Axon was much nicer. We've got the squares. And so what I did at first, I just wanted to make sure I had 100% accuracy when I trained this model. So I gave it one picture. And then I tested it with the same picture. And then I tried to predict the same picture. And it came out about 66% accurate. I was like, okay. So then I looked over here and I noticed that some of those squares have numbers and letters. And that must be what's throwing it off because it doesn't have enough, it hasn't seen all those pieces on those different squares. And so we've got perfect input, right? Might as well give it perfect training data. So I just put all of the pieces on, and then for every letter and number, I went through every piece of every color for white and for black. And that covers everything. And each image of those training data, the name of the files were the fin that represents that. So I'll go over fin for a little bit. There's a position part of fin, which everything is separated by a /. That's the rank. So the very first one is rank 8, and it goes all the way down to rank 1. And you've got lowercase letters are black, uppercase letters are white, and it's just rook, knight, bishop, queen, king. And the numbers represent empty spaces. So if you do your first move to e4, there's an example. The only thing that's changed are the ranks in the middle. You've got 4 empty spaces, then a white pawn, then 3 empty spaces, and so on. So to do training, we want to load all those board images, detect the squares of those images by going through the same stuff I just showed you, then convert them into labeled tensors, and then batch them up to do it. So in order to, we've just load those images, we get the image and the fin from the name, and in order to make labels for them, we're using hot encoded labels, so we've got all 13 things that a square could possibly be, the same things I just went over, and 1 represents an empty square. So, for example, here's a map from white rook is that bit string, and it goes all the way through with the 1 just going on. And then there's also a fin map saying, like if I have this square, and we know it's G3, from this given image that I'm training on, that's an empty space, it's 1. A2 is P, and you can map that back to its label. So you read those in, and that's how you can label them with those maps. And the fin map is generated. It takes that string and strips it down into that map, which is actually kind of complicated. I don't have the code for that, but there's a QR at the end that you can go to the repo and look at all this if you want. So once we have those, here I'm using pixels to read in the file, which only works on Linux, by the way, unless you set an environment variable for it to be on a Mac. A struct called square that takes pixels, and also some other things. But you give those squares, you map over those squares, get their pixels. That's what the pixel looks like. The image comes in as a bit string like that with random numbers up to 0 to 255. Turn it into a tensor from binary of bytes, then reshape it. Pixels gives you data that's in 4 channels, so that's what the 4 is for. This is 4 channels, and here's the height and the width. And then it goes over that tensor and divides everything by 255, so all the values become something from 0 to 1, which works better in model training. So then you have your tensor and your label, which is also another tensor. So it's a list of those things. And here are the results. So it turned out to be 40 different images, 8 for validation, 10 for test. And on epoch 8, I hit 100% accuracy. Yes. Like a glove. Fits like a glove, which is exactly what I wanted to do, which is something you should never do in production. Now, here's the model part for prediction, training and prediction. I looked at several blog posts by people at fly.io and Dockyard, because I have 0 experience in this stuff. I'd never used Axon before. All of the docs, of course, for NX and Axon are superb. You can just go into IEX and H function everything, and it's everything you need to know. But basically, you start out with a super simple model, flatten it so you can have a dense layer, and use a softmax. Then you train it. Categorical cross entropy means that you've got that list of 13 things that it could be. It's one of those categories. That's basically what that means. And then there's an atom optimizer that does something. And then you're measuring the accuracy. Then you use a subset of your test data to validate. And then you train with the other training data using EXLA with 13 or 14 epochs, which wasn't even necessary. So then you've got that, you save that to a file. When an image comes in that you want to predict, it goes through the prediction. It predicts it, and then that returns a label or a value, a tensor of values, and then it just gets the largest one in there, which represents the index of where that value is, and then you can map that back to what it represents in that when we saw the labels, whether it's R, N, whatever. And then, so we've got that. Here's where I talked about actually taking those things and converting them into a fin string was a way more code than I thought it was going to be. So you can go look at it later. But that was also just as interesting because it's like lots of stream pipelines and stuff where unit testing is incredibly helpful. And then to actually render that fin string, you can use chessboard element. That's just a HTML JavaScript element there for the position attribute. Give it the fin. And then here is my live demo. I'd like to preamble this with how hard it was to get this done. So initially, I was trying to deploy it to fly.io, but because I was using a Rust NIF with OpenCV, just actually getting the Docker container to build properly, I was having lots of problems with. And so I was like, all right, whatever. I'll just do this locally on my MacBook. But because I use Arch, by the way, I did it all on my desktop, and when I came to my MacBook, pulled it down, nothing compiled because of lots of native stuff. So before I left my house, I took a video recording of me doing it on my computer, on my monitor, just as backup. So I got here, I finally figured out what the problems were, lots of environment variables, M1s, stuff like that, and I got it to compile. Right as I got it to compile and went to the web page and it showed up, I realized that the model wasn't part of the repo. I had ignored it. And I don't have any of my training data on this laptop. So I overturned one of the tables in there and said, well, I made a recording, and here it is. Pick a picture. That's the input. Push capture, bam. So on the left side is the input, on the right side is what was predicted. Let's see if I can pause it, yeah. Look how fast it is too. When you've got perfect input and perfect training. See, they're identical, 100% accuracy, love it. All right, so clearly the limitations are, it was essentially hard-coded on this data. It's an already squared image. Since it was squared, I added the border lines manually in a hack in the code that I didn't show you. It's got perfect dimensions on everything. The orientation is assumed, so A1 is always lower left corner, and the algorithm would not work on it if it were something else. It would assume that was A1. And then the pieces are all identical except for their color, and it's overfit on purpose. So things we could do with this are, Caitlin, in her talk, the way she was doing contours and the boxes, when she was showing the video of the boxes around it, I'm like, that's perfect. And it'd be even easier because there's just a single image, not a movie. When you take a picture of a chessboard, it's not square. Due to the angle, it has different dimensions. What you want to do is find that board and change it so that it is square and there's nothing else in the image, and then everything will work. And you just also have to train on way more than that one thing. Many different chessboards, whatever. Even on chess.com, if you wanted to have a different background, that would blow everything up too. Training on all that stuff would actually, is what you would need to get something out in the real world. But that takes a whole lot of time and tens of thousands of images. And that's basically it. I've got a QR code for the repo and a QR code for my Twitter. And thank you.